Hi folks, this video contains a little more geology than usual, but I present it in a context of understanding the very cool geological history of an area in northern Ontario and the geological influence on type and distribution of some boreal forest plants. Did you know there was an inland marine sea that once covered a large area of northern Ontario? And did you know that that marine sea was responsible for the creation of sandy beaches located up to 250 kilometers away from Hudson Bay or James Bay? And did you know those beaches are habitats for plants today? If not, perhaps this video will be of interest to you. In early summer 2022, my fascination with the relationship between geology and plants took us to an area close to the transition between the Canadian Shield and the James Bay lowlands in northeastern Ontario. This area is an ecotone between the James Bay ecoregion labeled 2E on this map and the Lake Abitibi ecoregion labeled 3E on the map. When looking at the Google Earth satellite images and the geological maps produced by Ontario Geological Survey for this area, two things caught my eye. First, I had never been to this area, and second, the superficial geology of this part of the area was very sandy. I thought it might support some unusual plants. While this trip is not generally considered to be a top tourist destination, especially in late spring, when the hordes of mosquitoes and blackflies seek fresh mammalian blood, the area has a special appeal to me as a geologist with an interest in plants. While I was not disappointed by the geology of the area, I confess that I did not see any rare or unusual plants on the sand plain. So let's take a look at the geology and some of the plants that I saw in mid-June in this boreal jack pine lichen woodland forest. This is the Google Earth satellite image that caught my eye. There are 4 bands of light-colored material that looked like sand separated by low-lying muskeg. These were the areas I wanted to visit. The superficial geology of the area is illustrated here. Each color on this geological map by the Ontario Geological Survey represents a different type of geological material. Some of those materials belong to the Canadian Shield rock, but most formed during and after the last ice age. The pink-colored map areas are dominated by Canadian Shield bedrock, which is the oldest geological material in the area. These rocks are 2,000 million to 3,000 million years old. Lying on top of the Canadian Shield rock are glacial deposits of sandy silt and sandy till, which formed at the base or along the edge of the glacier. These are colored green on the geological map. These till deposits formed in the last 75,000 years. Lying on top of the glacial deposits are silt and clay-rich deposits that formed on the bottom of a marine sea or lake that formed in front of the melting glacier. These are colored blue on the geological map. Sandy beaches formed on the shores of the lake and shallow sea that covered the land after the glacier melted. These are colored yellow on the geological map. Locally, red colored lines mark the crests of beach deposits. These beach deposits that are colored yellow and red were the focus of my visit. The deposits that formed at the bottom of the marine sea and the beach deposits formed about 7,500 years ago. The gray-colored map areas represent organic fen wetland deposits consisting of wet peat, muck, and marl. And finally, present-day deposits of sand and gravel deposited by the Matagami River are colored brown on the map. These are called fluvial deposits. The fen and river deposits are forming today. All of this may sound a bit confusing, but the descriptions illustrate how a geologist can read 3 billion years, that's 3 billion years, of geological history in the area. Sort of makes you want to become a geologist, doesn't it? I visited the northern sandy band. In detail, this area is further subdivided into 2 sandy bands, separated by muskeg, as shown in this image. Note that the distribution of geological deposits is very generalized on these geological maps. The sandy beach deposits likely formed along the shore of an ancient sea called the Tyrell Sea. What? I can hear you asking, what was the Tyrell Sea? And what's with the ancient beaches? And what do they have to do with the types of vegetation in the area? To answer those questions, we need to understand a little bit of history of the last ice age. At its peak, the Laurentide ice sheet covered all of Ontario and extended into the northern United States, as shown on this image. The ice sheet was very thick in places. This cartoon shows estimated ice thicknesses of the Laurentide ice sheet at the peak of the Ice Age about 21,000 years ago. The ice sheet was up to 3 kilometers thickness, for example, over the city of Montreal. That's a lot of ice. What impact did that thick ice sheet have on the surface of the Earth in North America? Well, let's use this fluffy Earth as a model and these rocks to represent the thickness of the ice sheet. As the ice sheet grew and grew and grew, look what happened to the surface of the Earth. The weight of that ice depressed the surface of the Earth. It pushed the surface of the Earth down. As the ice melted, it got thinner and thinner and thinner. The surface of the Earth rebounded towards its original shape prior to the Ice Age. So ice accumulated, the surface of the Earth was depressed. As ice melted, the surface of the Earth rebounded. Now, the surface of the Earth rebounded more slowly than did the melting of the ice. And in fact, the surface of the Earth is still rebounding today. In the Hudson Bay area, the Earth is rebounding at about 1 meter every 100 years. That's pretty fast. So, that's the impact of the thick ice on the surface of the Earth. The term that geologists use to describe the land returning to its pre-glacier load shape is isostatic rebound. This process is summarized in this simple cartoon. The weight of ice depresses the surface of the Earth. When the ice melts, the land returns slowly towards its original shape. The land we call Ontario in Canada rose quickly immediately after the ice sheet melted, but the land rebounds much more slowly compared to the disappearance of ice. So even though today the ice has completely melted and no longer covers Ontario, the land across central and northern Ontario continues to rise up slowly. In this photo, I am standing on the shore of Hudson Bay, north of the community of Fort Severn, in the homeland of Moose Cree First Nation. Did you know that the shore of Hudson Bay is rising at a rate of about 1 meter every 100 years? That's right, new land is created as the rising land sees sunlight for the first time in 100,000 years. That is not fiction, it is fact. We can measure the land rising today using sensitive instruments. So, as the Laurentide ice sheet melted away, another interesting part of the land history took place. An inland marine sea flooded the area that was once covered by ice. Roughly 9,000 to 8,000 years ago, as the Laurentide ice sheet melted back toward Hudson Bay, the ice sheet split into 2 lobes. One lobe was centered over Quebec and Labrador, the other over the Keewatin area, as shown in this image. The split allowed a new and temporary marine sea named the Tyrell Sea to flood inland and cover the depressed land that was now ice-free. You can think of the Tyrell Sea as another name for the prehistoric or ancestral Hudson Bay. The Tyrell Sea existed only during the last stages of the retreat of the Laurentide ice sheet. The Tyrell Sea filled the basin created by the weight of the Laurentide ice sheet. About 7,000 years ago, and because the basin of depressed land was so large, the Tyrell Sea achieved its maximum extent, as shown in this image. That maximum extent was much larger than the modern-day Hudson Bay. But you may still be wondering, what does this have to do with the beaches I visited near the Kipling hydroelectric generating stations? Well, let's move on to the next chapter to find out. Given the presence of the temporary Tyrell Sea, you would expect to see evidence of an ancient shoreline that formed around the edge of the sea. And in fact, that is exactly what you see when you fly over the area. I photographed these bands seen in this photo when flying over northern Ontario. The dark bands are lines of old Tyrell Sea beaches. The beaches are dramatic in winter because conifer trees grow on the sandy beach. Conversely, Muskeg is largely devoid of tree cover, so the ice and snow stand out as white strips. Each dark line represents a former seashore of the Tyrell Sea. As the land continued to rise, the Tyrell Sea shrank back towards the present-day Hudson Bay, and beaches continued to form closer and closer to the present-day Hudson Bay shore, as seen in this photo. The frozen Hudson Bay is the flat white area at the bottom of the photo. This video shows the dramatic bands of beaches just south of Hudson Bay, near Fort Severn. In summer, the sandy beaches are still distinctive because of the color contrast between the darker green conifer trees that grow on the beaches and the lighter green muskeg vegetation. The conifer trees that grow on the tops of the sandy beaches are darker green in color compared to the low, wet muskeg that grows between the beaches. Geologists call these raised or stranded beaches. And to reiterate, these beaches represent the former shorelines of the Tyrell Sea that was created as that sea shrank back towards the present-day Hudson Bay. And recall also that the older Tyrell Sea shoreline beaches occur up to 250 kilometers farther inland than the present-day Hudson Bay shore. Modern beaches are still forming today along the Hudson Bay coast because Hudson Bay is rising at a rate of 1 meter per century. Quite amazing, isn't it? So in answer to the question, what does all this have to do with the sandy bands that I visited west of the Kipling Generating Station? Raised or stranded beaches of the type I visited near the Kipling Generating Station started to form about 8,000 or 9,000 years ago on the shore of the ancient Tyrell Sea, considered to be the ancient ancestral Hudson Bay. As the land rose due to isostatic rebound, successive shore beaches formed as the Tyrell Sea shrank back towards the present-day Hudson Bay. Older beaches were stranded farther and farther from the seashore as the land continued to rise. How cool is that? That sandy substrate of beach habitat that I walked on during the summer of 2022 is the home to several plant species. That habitat began to form towards the end of the last ice age, when the Laurentide sheet retreated towards the north, split into two lobes, and that allowed the incursion of the marine Tyrell Sea. That's a bit of a mouthful and a bit of a history, but let's now look at the beach habitat. I'm heading out to see if I can find a raised beach. I'm a little worried because I've got to go over there, and there's a swamp between me and where we are, so we're following this old road to see if it gets us to a location where we can cross that wet spot. So first obstruction, there's the road, here's the creek, there's the beaver dam. I think we should be able to get across right here. Looks a little slippery. So the strategy is to walk past the point of interest to see if the beachy stuff intersects this old road, and if not, we'll walk back and then take a beeline through the bush. We'll check out some of these side trails in case one of them heads over to the area of interest. This one has potential. And there's a little knoll. That's encouraging. So this looks like the area of interest. Open, this is what I could see on Google Maps, was an open area. I'll first walk the length of it, following this old road, and then walk back to see if there's any interesting plants in this open area. Some of these raised beaches formed 5,000 to 6,000 years ago when the land was flooded by the ancestral Hudson Bay. And they have sometimes in the far north, I've seen some quite interesting plants on these raised beaches, which is what I'm here to check out. And also to see if there's any beach geological features. So the road took a branch. This branch, just checking it out, went down to the low area. It's quite wet, swampy, lots of moss. So I'm not going to go too much further on this one. I wonder if they're old winter roads But this is as far as we'll go on this one because it's getting pretty wet and I'm not equipped for that. So we'll take a few pictures here of spruce, tamarack. Don't see any balsam. And I'll look a little bit more closely at the ground. See if there's any plants, flowering plants. I share two drone perspectives of this area. This view, looking down, starts on a sandy beach deposit and crosses over Muskeg with standing water to a second sandy beach deposit to the north. The wetland merges with Muskeg of the previous video. This view, looking east, shows the two sand beaches separated by the wetland. In the distance, you see the Kipling Generating Station located on the Matagami River. I looked carefully for signs that these features were anthropogenic in origin, that is, created by human activity. I was not convinced, but it is possible that there is some anthropogenic disturbance of the area. It's an attempt to illustrate the rather abrupt rise from the lowland area on the left to this what could be a raised beach. On the right, you can see there's lots of sand. There's cobbles, rounded cobbles, up to 5 or 6 centimeters, rarely 20 centimeters. And this is what the road is built on, this raised sandy cobbly deposit, which I'm assuming is a raised beach. And an illustration of a cattail marsh lying in between this raised sandy knoll, raised sandy line. Lots of cobbles. I don't think this is disturbed. So we're in a spruce, jack pine, lichen habitat. Interesting. You can see little game trails here running across the image. There's several. Probably red squirrel. There's another one. Running from tree to tree. Jack pine in front of us. And spruce in the lower growth. White spruce, I'm assuming. So we're in a much broader area, almost a plain that you can tell, old road, very sandy. Lots of jack pine, some lichen, blueberry on the floor. Bear bells ringing in the background. So we'll go and have a walk and see where this one takes us. So just a reminder, this is a sand plain, lots of jack pine, some spruce, blueberries, lichen. There's Saskatoon berry, service berry, pincherry I've seen. Quite lovely, easy to walk. DC-3 just flew over. We'll just have a look out here. So this is there's some birch, jack pine, black spruce. And the substrate is very sandy. Lichen blueberries, Saskatoon berry, bunchberry, pin cherry in this habitat. And trembling aspen. More of the sand plain with jack pine, a few white spruce, very sandy soil. There were no exotic flowers that I saw, no exotic trees that I recognized, no moose, no ptarmigan, no bear, which is a good thing. Well, there were bear tracks, but they weren't, and bear scat, but nothing was recent, which is a good thing. In the final 2 chapters, I leave you with some images of the plant and tree vegetation, including lichen, that I saw on the sand beach substrate, followed by plant and tree vegetation that I saw on the edge of the wet, mossy muskeg that occurs between the sand beaches. Enjoy! Well, this draws the video to a close. Recall that I am not a botanist, but the plant species identifications have been confirmed using iNaturalist. Also, I have greatly simplified the geological story, because the video audience includes many expert people, but not necessarily geological experts. Therefore, forgive me for the geological simplifications. If you've learned something or enjoyed the video, please consider subscribing and liking the video. That will help YouTube direct others to this and other of my videos. Thanks very much for sticking to the end. Bye for now.